And then what's usually given as a companion to that is the following: a mapping T from Rn into Rm is 1 to 1. Let me put little dashes here. If for any uv in Rn where T of u equals T of v, then u equals v. One-to-oneness in the world that you're probably used to, where you're dealing with real valued functions from R to R, the one-to-one functions were the ones that passed the horizontal line test. These were precisely the ones that had inverses. Another way to put it, let me put it this way, that is, for any vector in the range of T has exactly one vector that is mapped to it. Let me show you what I'm talking about here. Suppose T of x equals, I really don't care, let's call it y, but T of z also equals y. Then if it's 1-to-1, this implies that x and z were actually the same vector. So there's only one vector that maps to each vector in the range. That's exactly what 1-to-1 means. Let's use that previous example, T of x1, x2, x3, x4. That was 2x1 plus 3x2 minus 4x4. Is this mapping 1-to-1? Well, actually, no. I sort of mentioned it in the previous one. If you take a look at this vector, T of, let's do 1/2 with all zeros after it. According to the formula, that's 2 times 1/2 plus 3 times 0 minus 4 times 0, which equals 1. On the other hand, T of 0, 1/3, 0, 0 equals 2 times 0 plus 3 times 1/3 minus 4 times 0, which also equals 1. So I have T of 1/2, 0, 0, 0 equals T of 0, 1/3, 0, 0, but 1/2, 0, 0, 0 is not the same thing as 0, 1/3, 0, 0. So this implies T is not 1-to-1. Let's try another one of these things. Here, the formula that I'm going to give you looks like the following. T of x1, x2, x3 equals x1 minus 5x2 plus 4x3. The second entry is x2 minus 6x3. So I have the two questions. Is t 1 to 1? Is t onto? Well, I don't know. Let's take a look. So for the 1-to-1 part, I'm going to look at something like this. Suppose I have t of x1, x2, x3 equals t of y1, y2, y3. So let me use my formulas. On the left, I have x1 minus 5x2 plus 4x3, x2 minus 6x3. y1 minus 5y2 plus 4y3. And then I have y2 minus 6y3. Now, unfortunately here, I can't really compare whether I want to determine if x1 equals y1, x2 equals y2, x3 equals y3, and it's almost impossible for me to tell. Instead, let's do something a little bit different. Notice that I can do this. So let me just say this is difficult, if not impossible, to determine whether the x vector equals the y vector. So this is difficult to determine if so instead, let me go ahead and take a look at the matrix for this. So remember, it's little practice and you'll see that you can make this up here. If you can see, here's how the matrix looks like for it. You can see I got an x1 in the first entry, but nothing in the second entry for x1, that is. So I'll have a 1, 0. Then for the x2s, I have a -5 and a 1. And then for the x3s, I have a 4 and a -6. Now, suppose that that is equal to, I don't know, some b1, b2. So this will be a b vector off in the rangeland. Well, this, of course, I can set up as the following. An augmented matrix, of course. I can stop right here now. If you look, here is a pivot and here is a pivot. Unfortunately, here, this column here means that x3 is a free variable. If it's a free variable, then I most likely have an infinite number of things that will map to b1, b2. So thus, we have multiple vectors that map to b1, b2. So you can see going to the matrix going to the augmented matrix has provided us with a very powerful way of determining whether it's going to be 1-to-1. I showed you that trying to do it directly was very difficult. But once we have the idea of free variables, we know what we're talking about then. Therefore, t is not 1 to 1. Verify this for yourself. If I try to do t of 1, 0, 0, that will actually equal t of -25, -6, 1. And of course, since those vectors are not equal to each other, you can see that by the definition, it's not 1 to 1. But I thought it'd be a lot easier to do the free variable. Let's move on to onto. Let B in where we at R2 be any vector in R2. And you know, what I want to do here is show that something maps to that B or that something doesn't map to that B. Well, let's see what happens. So once again, we are trying to figure out if this is true. And of course, let me go ahead and put in my augmented matrix again. That was 1, 0, -5, 1, 4, -6, and let's go ahead and do whatever row operations. Well, there's really only one that I can do to achieve echelon, and that is to take out this -5 here. So I'll do 5R2 plus R1. And let's see, 5 times -6, -30 plus 4 will be 26. And then I'll have B1 plus 5B2. And then I still have a -6 here, B2. Now it's easy to see that I'm going to have a solution. Actually, I didn't even need to. Perhaps I will use this as an instructive method. I didn't need this. Instead, this guy is good enough for me, because right here I have x1 equals 5x2 minus 4x3 plus b1, and x2 equals b2 plus 6x3. So yes, I'll be able to find numbers for x1 and x2 for which this is true. So t is onto. Now, the important thing in all of this was to look at these guys. For the first part, I looked at them, and the second part, I kind of looked at them and saw the same thing. I want you to notice something here. T was onto, and I had pivots in both rows. So this is a theorem I'm going to do in a second. Both rows had pivots. Now go up to 1 to 1. Here, it turns out that you need to have pivots in every column for it to be 1 to 1, and we did not have a pivot in the third column. This next theorem gives us sort of an easy way, the easiest way to tell when something is 1 to 1. So let's let T from Rn into Rm be a linear transformation. T is 1 to 1 if and only if the only solution to t of x equals the zero vector is the trivial solution. Let me do the proof. And once again, since it's an if and only if, there's two directions here. First, we make the assumption of whatever is before the IFF, and that is we are going to assume that t is 1 to 1. Then if t of x equals the zero vector, then t of x also equals t of the zero vector. So since we're assuming that t is 1 to 1, this immediately implies that x equals the zero vector. So this is since t is 1 to 1. So the first direction was very easy. Remember that for any linear transformation, t of 0 is equal to 0 as well. So that's why I knew that t of 0 was equal to t of x, because I was assuming t of x was equal to 0, the zero vector. Now let's go in the other direction. Assume that the only solution to t of x equals the zero vector is the trivial solution. Now then, suppose we have t of x equals t of y. Well, that means that t of x minus t of y is the zero vector. But now t is a linear transformation, so I can make this t of x minus y. And since the only solution is trivial, we are forced to deduce that x minus y is equal to 0, since there's only the trivial solution. Well, then this implies that x equals y. So then, therefore, t is 1 to 1. And that completes the proof. Another theorem. Let t from Rn into Rm be a linear transformation. And let A be the standard matrix for T. Part 1. T is onto if and only if the columns of A span R to the M. 2. T is 1 to 1 if and only if the columns of A are linearly independent. So let's go ahead and do this proof. It's lengthy just because there's a lot. Each of these is an if and only if statement, so each of these has two parts. And they're really not that long. Each part is not so bad. It's just lengthy because there is a lot of writing involved, but not a lot of detail. I mean, a lot of writing is there, and there's a lot of important details, but none of the stuff that I'm going to do is difficult. So let's assume that T is onto. Let B be any vector in Rm. Then there exists a vector x in Rn such that T of x equals B. That's what it means to be onto. I have something that maps to every single vector in the codomain. So now that I have a T of x goes to B, I'm going to change this to AX equals B. Remember, A is the standard matrix for T. Right? Now, if I go one step further and I write my x as x1 ... to xn, like that. Remember the first definition that we had for multiplying a matrix. Oh, actually, wait, I got one more step. I didn't. Get out of there. I can write the matrix A like that, where each of those A sub I vectors is a column. Now, according to the definition of multiplying a matrix times a vector, we can break this out in the following way. Well, since this means that B is a linear combination of the A's, this implies that B is a linear combination of the columns of A. You can see it right there. We have a scalar times the first column plus, and you can figure out the middle stuff, scalar times columns. So that's the breakdown there. So that way wasn't so bad. Now let's go and do the reverse way. This time we're going to assume. Now let's come back to what it said in the theorem. It said that T is onto if and only if the columns of A span R to the M. So this time we're going to assume that R to the M equals the span of A1 up to AN. Let B be any vector in Rm. Since then B is in the span of A1 ... AN, there are scalars, let's call them x1 up to xn, such that B is a linear combination of those things. That's the definition of B being in the span of those things. And of course, I can break this out as A1 to AN times X1 to XN which of course is AX, which of course is T of X. So of course the X I'm talking about is this particular X right here. And so this implies that T is onto. So we took care of the first part of the theorem. The second part of the theorem said T is 1 to 1 if and only if the columns of A are linearly independent. So for this proof, first we'll assume this direction. Assume T is 1 to 1. Suppose x1 up to xn are all real numbers such that x1 a1 plus plus xn an equals the zero vector. Remember, I'm trying to show that the columns are linearly independent, so I want to show that each of these scalars actually equals 0. Well, just in the like last time, we have the following then. I can do x1, x2, xn times a1 up to an, and that's equal to the zero vector. And of course, this is T of X equals the zero vector. Now, since T is 1 to 1, we only have the trivial solution. That's the last theorem. Trivial solution, which was x was equal 0. Well, x, of course, is that vector x1 to xn, so that means every single entry for x is equal to 0. And that, of course, implies that the columns of A are linearly independent. Now let's go for the reverse. This time we're going to assume that the columns of A are linearly independent. Suppose T of X equals 0. I can show that T is 1 to 1 if I can show that the only solution here is the trivial solution. And you can see this is going to be very, very simple. The T of X I'm going to break out as AX equals 0. And as before, I'll have A1 up to AN times X1 up to XN equals the 0 vector. And of course, this means x1 a1 plus dot 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 plus xnan equals the 0 vector. And we know this implies that x1 equals x2 equals dot 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 equals xn equals 0, since the columns of A are linearly independent. This is the assumption I'm making for this part. Well, that implies that the x vector is the 0 vector. Therefore, t is 1, 2, 1. As an example, suppose t from R4 into R3 is a linear transformation. That is also onto. Let A be the standard matrix for T. Describe the possible echelon forms of A. So let's see what we have here. Since we are going from R4 to R3, notice that A is a 3 by 4 matrix. So keep that in mind. 4 columns since R4 is the domain, 3 rows since the range is inside of R3. And let's take a look then at some various echelon forms. So we have 4 columns, 3 rows. So I could do something like this. And then I can have this. Remember, these stars don't matter. The blocks, though, are non-zero items. They're meant to be the pivots. Now, if on the other side I had something like a B1, B2, and B3, remember this is supposed to be onto, this would have a solution because all I'd have to do is subtract star and divide by whatever the block was. Here, I subtract those 2 stars and divide by that block. I subtract these 3 stars and divide by that. The important thing is that I will get, for every B1, B2, and B3, I will get a solution for X3, X2, and X1, as long as it follows some sort of a staircase like this. So I'm always going to be imagining those B's on the outside of it. Let's take a look at another thing that can happen. We could have this, and then you could skip a space. So like I could have a star here and then zeros underneath, like so. And once again, you can see if I had a B1, B2, and a B3 out here, well, this would be easy. All I have to do is divide by that block to get what X3 was, subtract star, divide by block to get X2. So what I'm getting at is I have a solution. It may not be unique, but I have a solution for X1, X2, and X3. Let's continue. What are some other ones that we could have? We could have done something like this block. Then I could have had the next block right under and below it, like this. But then I could skip a block and have a 0 here, but then this block here. And once again, if I put these here, convince yourself that I will have solutions. I will be able to figure out what x3 needs to be. I will be able to figure out what x2 needs to be, and I will be able to figure out what x1 needs to be in order for this mapping to occur. Almost done. There is one last possibility here. Notice that we have 1, 2, 3, 4 columns. That means there's 4 variables. But since the range is inside of R3, we only need to fill up 3 spots. So we really have more than we need. One thing that you could do is this. Block, 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 stars, 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 0, 0, 0. But then this can happen. That means that x1 just happens to be free. But once again, if I put these here to let me know if I can solve for it, I can. You can see I'll be able to find an x here. In this case, an x4 I'll be able to solve for. In this case, I'll be able to solve for an x3. In this case, I'll be able to solve for an x2. Which reminds me of the last problem. I think I may have called this guy an x3, but it's really an x4. x4, x3 was free. I mean, you're going to have a free variable no matter what. So you'll have more than one solution, as a matter of fact. x2 and the x1. So if I misspoke, make that adjustment in your notes. Now, in the current book we're using, these videos were made to be used with any linear algebra book, but it happens to be the one that we're using right now. I have a couple of theorems that I want to include that I didn't really see mentioned, at least not as mentioned as strongly as I hope they would be in the textbook. So let me go ahead and do these. They're a little bit lengthy, but once again, they're not difficult. So this theorem goes like this. AX equals B always has a solution if and only if A has a pivot in every row. And it's a dreaded if and only if situation, of course. So let me go ahead in the forward direction. Let us assume AX equals B always has a solution. That means you'll always be able to figure out what X is. All right, so let's go ahead and take a look at any row. So pick any row of A. Say row I. Let B be in Rm. I didn't really say it, but A, it matches the linear transformation. So A is going to be an M by N matrix, just like linear transformations that go from Rn to Rm. So keep that in mind. So anyways, I want to let B be in Rm such that if I start with the augmented matrix A slash B and I perform row operations to get to U slash EI. So let B be that vector such that when you take it, start with it, and do the row operations, it ends up having a 1 in the ith spot and zeros everywhere else. And this is where U is an echelon form of A. We know that row I must look like and then you'll have a block. So you have leading zeros, a block, and then maybe some stars after it. But at the end of that row, after the vertical line, you'll have a 1. In other words, I can't have all zeros in that row. Let me put it that way. That is, row I of U cannot be all zeros. So row I must have non-zero entries. That first non-zero entry is a pivot. So therefore, row I has a pivot. And since I was arbitrary, that means that every row of A has a pivot. And let me stop there for a second. I may have talked without saying every last detail that I want to. Remember, the pivots, the ultimate pivot positions, are locatable only when you get to the echelon form. Most of the time you can't locate them with the original matrix themselves. But nonetheless, the pivot positions are located in the echelon form. But then when you go back to A, those same positions are considered the pivots in the matrix A. So this just means that if every row of U has a pivot, every row of A has a pivot. So that takes care of one direction. Now let's go in the opposite direction. This time we are going to assume that A has a pivot in every row. Now what I want to do is show that it's onto. Let B be in Rm, and basically I want to, when I say onto, I mean I want to show that AX equals that particular vector has a solution. So I want to show that AX equals B has a solution is what I want to get to. All right, so when we run through A, B, U, let's call it D. I don't know what it's going to look like when all is said and done, but let's just say the echelon form is U and D is something. We know that every row of U has non-zero entries. Since every row has a pivot. Well, what does that mean? That means that we have no rows of 0. So if that's the case, then we automatically know that this thing has a solution, which implies that B has a solution. Since B in Rm was arbitrary, AX equals B has a solution for every B in Rm. Next we have something called a corollary. This is usually something that follows pretty quickly from the theorem. So let me show you what I'm talking about. Let T from Rn into Rm be a linear transformation. Let A be the standard matrix for T. T is onto if and only if A has a pivot in every row. And all I got to do is take the T of x equals B and turn it into AX equals B and apply the theorem. So it's a very easy corollary to prove. Usually corollaries are fairly easy. They're usually easier than the theorem that they're based on. That's, I think, about the last of the theorems for this massive section. Suppose T from Rn into Rm is a linear transformation. Let A be the standard matrix for T. T is 1 to 1 if and only if every column of A has a pivot. So it's a nice companion piece to the previous one. All right, since this theorem is an if and only if theorem, the first thing I'm going to do is the forward direction. So I am going to assume that T is 1 to 1. Thus, T of x equals 0 has only the trivial solution. Well, break this out into AX equals 0, using the standard matrix for that. Thus, there are no free variables, because I only have one solution. Free variables indicates more than one solution. So now, if you take A/0, that augmented matrix, run through the row operations to arrive at a U/0, what does that U look like? Well, it has to look like this. When I write my blocks, they have to go down one in a diagonal fashion. Why? Because if they skip, if any of these were to skip a space, we would have stars and we would have no pivot, and that would mean that we'd have free variables. So they can't skip any columns. Now we could, let me put my zeros over here. I'll put a 0 way down here. Because what could happen is, I don't care about up there. And of course you can have zeros down here. But even the last one, you can have zeros down there. I mean, you can have rows of zeros. That's okay. But you can't have columns that do not have a pivot in them. So this implies there is a pivot in every column of U, which means there is a pivot in every column of A. So I took care of that direction. Now let's go in the reverse direction. Let's assume that every column of A has a pivot. Then we have no free variables. Thus, AX equals 0 has only the trivial solution. Therefore, T is 1, 2, 1. Final example. Suppose T from Rn into Rm is a linear transformation. 1. If T is onto, how are M and N related? 2. If T is 1 to 1, how are M and N related? All right, well, let's take a look at the situation where we have an onto. Since T is onto, we have a pivot in every row of A. So think about how they work, these pivots. A is, let me see, M rows by N columns. So let's take a look at the pivots. We have to have a pivot in every row. They could do whatever, but when the pivots go down and move, they've got to go down and to the right. Well, how far can we go? If we have a pivot in every row, then we have a total of M pivots. Now, since we're moving down and to the right, there has to be at least as many columns as there are rows. So, if we have to have at least as many columns as rows, that means that N is greater than or equal to M. Now this part, what if it's 1 to 1? So in this case, we must have a pivot in every column. Well, if you think about that, if we have to have a pivot in every column, once again, I need one in the first column, I need one in the second column, dot, 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 and I got to have 1 in the nth column. But as I saw from before, it's okay if we have zeros after that. You can do that. So in this case, we need at least as many rows as columns. So in this case, m is greater than or equal to n. One last thing. If t is 1 to 1 and onto, then m will equal n, and you'll have a square matrix.